first year mechanics, which is called gravitation. So remember, it's a sort of an advice I would like to give you, that if you study gravitation properly, your chapter electrostatics is almost completely done, right? So the chapter gravitation, which is in your first year or in your 11th class, and the chapter electrostatics are almost the same. If you replace a mass by a charge, right, all the concepts that you learn in gravitation will simply apply to electrostatics. All the concepts that you learn in electrostatics will simply apply to gravitation. Doing one of them perfectly ensures that the other as well is done, right? So that's why focus on the concepts of one and you'll be done with both actually. So we'll be discussing the gravitational potential today. Right, gravitational potential. So here we have a mass m. All right, this mass will have sort of a gravitational field around it. At the value of the gravitational field at a distance r, the strength of the gravitational field at a distance r can be calculated by using Newton's law of gravitation, right? So whatever it is, it has a gravitational field around it. This field is conservative in nature. That means if I take a mass around a closed path, I will do zero work, right? So basically, integral gravitational field dot product dl. If your dl is a closed path, it will be zero. That means if I take a mass and I go around a closed path, the net work done by the gravitational field will be zero, right? And in fact, if you take it very, very slowly, the work done by the external force also will be zero, because work done by external force plus work done by gravitational force is equals to delta Ke by work per energy theorem, like work energy theorem, right? If you take it very slowly, that means you're not providing it with any velocity, either in the beginning or in the end. So this delta Ke is essentially zero, because initially it was zero, final also it will be zero. That means work done by your external force equal to negative of work done by gravitational force. Always remember this. But this is true only when you take the body or you move the body very, very slowly. That means giving it negligible kinetic energy, right? This is what your gravitational field is. So basically, around this field, every point in space will have a gravitational potential associated with it. Gravitational potential associated with it. So to be fair, I can't find the absolute value of a gravitational potential at a point. Did you understand the statement? If I have this point, I can't find the absolute value of the gravitational potential at this point. I cannot. But what can I find? I can find the gravitational potential at this point with respect to some other point, right? So if I assume that gravitational potential if the gravitational potential at infinity is zero, then I can find the value of gravitational potential at this point with respect to infinity, being zero. But if I don't specify, like if I don't fix the value of a gravitational potential for some point, then I can't find the absolute potential at this point, right? So let's see, what is the definition for gravitational potential first of all? So the definition goes like this: it is the work done to bring work done by external force. Remember the keyword external force. It is the work done by external force to bring a unit positive, or basically a unit mass is anyways positive, right? to bring a unit mass or 1 kg mass, if my unit is in kgs, from infinity to that point. So the work done to bring 1 kg of mass from infinity to a point by an external force is called the gravitational potential at that point. Remember, and in fact, yeah, there is one more thing. Very slowly. You have to remember this very slowly. There are two key terms here. You have to bring 1 kg mass from infinity to a point. The force that brings this mass has to be external, and it has to bring it very slowly. When these two happens, like the force is external and it brings it very slowly, then the work done by that external force is the gravitational potential at that point. Remember this. So let's derive the expression for this. So you have a mass m, capital M. Let me fix potential at infinity to be 0. Right. So I'm deriving it now. Let me fix potential at infinity to be 0. I've fixed the value of potential at infinity to be 0. Now, I'll take a 1 kg mass. I'll let it be at a distance x. Look at this point. Let it be at a distance x from the mass. Right. At x, what is the force that this body will experience? The gravitational force that this 1 kg mass experiences is gm into 1 by x square to the right, or to the left, sorry, because this mass will try to attract the 1 kg mass, right? That's universal, like law of attraction, right? So this is the force that will try to attract, it will try to pull in. So in order to make sure that you bring in the mass very, very slowly, your external force has to be equal and opposite to this, right? Why should it be completely equal? Why should your external force be equal and opposite to Fg? Because the net force on the body has to be 0. You have to bring it very slowly, right? If it's unequal, then the body will have an acceleration and then it will not come slowly. You have to bring it very slowly. That's why this term very slowly is very important. So this is your external force. So your external force is in this direction, but your displacement is in this direction, right? Because the body is actually going closer to the mass. You are bringing it from infinity to this to m, right? So you're to x. You are bringing it towards m. So work done by external force is minus integral so remember this is the direction of your dx, right? But your x you are measuring from here, right? So dx will have a negative sign. So simply it will be gm into 1 kg by x square, right, into dx. And you'll have a minus sign. And your x is measured from infinity to this point. So x starts from infinity and comes to x, right, at a distance x. So when you integrate this, it's very, very simple, this integration. It's minus gm by x. So you have an infinity to x. So it will simply be minus gm by x. Interchange the limits x to infinity. Oh, I forgot about the dx, about the negative sign of dx. Dx will also have a negative sign, right? Because your x is measured from the mass, but your dx is in that direction, so it will also have a negative sign. So that negative will compensate for this, and then you'll just have a plus here. So this will simply be gm by infinity will x. Remember that minus sign, right? So the minus sign exists. With this done, I guess we can start solving a few problems now. This was the theory. And remember, your F external will be equal to Fg. Why? Because you're bringing the mass very slowly. That is the reason why that term slowly is important. And what is this work done? This work done is by the external force to bring an object from infinity to that point, right? So, if this was your internal force, the value of gravitational force, if this was the work done by the internal force, that is basically your, not internal force as in the conservative force, which was your gravitational force, then the value of potential would be negative of this, right? But this is the work done by the external force to bring an object of 1 kg mass from infinity to this point very, very slowly, right? All this has to be ensured, only then this will be the value of the gravitational potential at that point, right? So, with this done, I can ask you a few things now to derive expressions for various gravitational potential functions for various bodies. Fine. Let's discuss about a uniform solid sphere. I'll derive it for a solid sphere because it's slightly complicated for a solid sphere. And then we'll discuss problems, because let me tell you, in fact, let me tell you about spheres because this question keeps coming again and again. What if I have a hollow sphere of mass m? What if I have a solid sphere of mass m? Right. So you have a hollow sphere of mass m, and I'll ask you two things about it for three conditions, right? So case one is for a distance r greater than or equal to its radius. Case two is for a distance r which is between which is greater than or equal to radius. That means at the surface or outside the surface, and r less than radius, right? These cases, I'll ask you what is the gravitational field. Remember, I'm asking you field, and then I'll ask you what is the gravitational potential. So let's see. Let's discuss about gravitational field first. So for case A, gravitational field is, what do I simply have to do? I have to assume that this mass is concentrated at the center. If the distance is greater than or equal to capital R, then I can assume this mass to be concentrated at the center, and then it will be something like this at a distance r. Remember, this r has to be greater than or equal to r, only then you can assume it to be at center, right? And then I'll calculate the value of gravitational field, and that's nothing but gm by x square, right? This is the field. You already know what field is, gravitational field, right? Coming to its potential for the same case, this is the field. Coming to the potential, for potential at the surface or beyond it, you will again do the same thing. You'll assume it to be at center, even for potential. And at a distance r, you'll calculate the potential. And remember, your r has to be greater than or equal to r, only then you can do this. But you'll have a minus sign, minus gm by r, right? We have derived it already. This was field and potential for case A. Let's discuss same thing, field and potential for case B. For your r less than capital R, right? Let's discuss gravitational field first. Now, can you assume, so if my distance is like this, like if I have a mass like this, if my distance is less than r, can I assume this mass to be concentrated at center if this is a hollow sphere? The answer is no. I will say gravitational field is zero, simply zero. if it is a hollow sphere of mass m, not if it is a solid sphere. If it is a hollow sphere of mass m, then inside the sphere you will have no gravitational potential, right? Remember, it will be zero. You can't assume it to be at center and then calculate this, like do the same thing as you did here, right? This is by r square, I'm sorry. You can't do the same thing in the second case if you are inside the sphere. What about gravitational potential inside? So you have to understand what you mean by gravitational potential. It is the work done by an external force to bring a unit mass from infinity to that point. So here, if I ask you what is the gravitational field at this point, the answer will be the amount of work an external force does. And what does it do work against? We have already seen in that diagram, it does work against the gravitational force that was trying to pull it, right? It does work against that. So first, I'll have to do work to bring a charge or to bring a mass of 1 kg from infinity to the surface, and then from the surface to inside. So basically, potential will be work done to bring from infinity to capital R, basically surface, and then work done to bring from capital R to small r. Now notice this term will be 0. Why? Because there is no field inside the potential, right? So there is no field because field inside the sphere. If there is no field inside the sphere, then it hasn't got any force to oppose, right? So it was doing work against the gravitational field. But if inside the field itself is 0, why does it have to do any work? I can just take this mass and displace it like this without applying any force, right? I don't even need to apply any force. So this term will be 0. So simply the potential is the amount of work that is done to bring this mass from infinity to the surface only, right? And to bring from surface to any point inside R, it will be same, it will be 0. So potential at any point inside R that means any point inside, it has the same value, is equals to potential at surface, right? Because only this much of work will be done, and that is minus g. Now you can assume it to be at center and calculate the potential at a distance capital R. So minus gm by r. This is the potential at the surface and at any point inside this hollow sphere. Now coming to solid sphere, a lot of things will change now. Remember, this case will remain the same for a solid sphere. So if I have a solid sphere of mass m, this is a solid sphere. If I have this first case A, where my r is greater than or equal to r, I can comfortably assume this mass to be at center. And then field at a distance r, gravitational field at a distance r will simply be gm by small r square if my r is greater than or equal to capital R, just like this case, and potential at a distance r, which is basically at surface or beyond it, right? Again, it is the same as this case. I can assume it to be at center, and then I'll have a minus gm by r. Things will change when you come inside, right? Things will change when you come inside. So I have a case B now. So for case B, what is the field? So that means I have a solid sphere of mass m, and at a distance inside, at a point inside which is at a distance r from the center, what is my value of gr here? Can I say it will be 0? No, because if you have a sphere like this, like a sphere of centers of radius small r, it has some mass enclosed inside this, right? So remember, this mass, only this mass which is inside this small sphere will have an effect on the potential. The mass that's this mass that you see will have no effect on the field. The mass which is outside that small sphere, right, in between the outer sphere and the smaller sphere, whatever the mass is there, this ring sort of a mass, that will not have any impact on the gravitational field at a distance r, right? If your r is less than r, only this inner mass will have. So I have to, and that inner mass I can assume to be at center, and I will say, let this inner mass be m dash. So you can assume m dash to be at center, and then at a distance r, you need to find the gravitational field. So g at a distance r is g m dash by r square. And what is m dash? M dash is nothing but density will remain the same, right? And you just need the volume of the inner sphere. So m dash is nothing but small r cube by capital R cube into capital M, and then you have a R square. You derive this yourself, right? M dash is nothing but density rho into the mass, the volume of the inner sphere. That's 4 by 3 pi small r cube. And rho is nothing but capital M by the mass of the total, by the volume of the total sphere. The difficult part is calculating the potential at this point to derive it. Alright. So, what about potential at a point R which is less than? So, will it be the same as this case? No. It won't be the same, obviously, right? Because this term will not be 0 now. It was 0 before, but now to bring it from surface to inside, it also has to do mass. It also has to do work, right? Because there is field inside the surface. So infinity to small r, infinity to capital R, like to the surface. And that's basically potential at surface. So that this expression will be the same. Like this will be the same for both this case and this case, right? But this will change. Dash by x square, right? If you have a sphere like this, and m dash is the mass enclosed inside. So this is the work, this is the force. If you bring it by a small amount, the work done, the small work done that you would do is this integral dx. And be careful with the sign here, because, right, but your force gm by x square will attract it inside, so your external force has to be completely opposite, right, to your displacement. So your displacement is in this direction, but your force is in this direction, so it will have a negative sign for that too. That means that negative sign and this negative sign will become plus, right? So just give me a while. So it is simply this. And this is the small work done to bring from x to x plus dx. This x will run from capital R, because you're bringing it from the surface, to a distance small r, because you're bringing it from surface to r. So like the upper limit of x is r, right? So calculate the value of this integral. Add that to the value. So this is the work done. This is w dash. You have to add w dash to this, and sum of these two is the potential at a distance small r, right? So derive that yourself. I think you have understood the method. So be careful, and it's really worth doing this exercise, right? Because you learn a lot from this. So with this done, we'll discuss a few problems now. We'll not discuss very complicated problems, because this derivation itself was very complicated. So, and trust me, you won't get anything of much greater difficulty than this, at least in your mains, because everything else is quite simple and direct. This was the only thing that required certain concept, right? I explained you the concept, and once you do it yourself, you'll remember it much better. It is done. Let's see what is the next problem we have. So, in fact, I'll give you a problem. You have a ring of radius capital R of mass m, a uniform ring. On its axis at a distance x, at this point, calculate the field at x, gravitational field at x due to this ring. The question is, how do you do it? The answer is very simple, actually. You take a small mass dm, calculate the value of field at a distance x. This is r. So this distance, like distance of that point from dm, will be nothing but under root r square plus x square, right? Just applying hypotenuse, like Pythagoras theorem. So the small field at that point due to the small mass dm is minus g times dm by under root r square plus x square. Right. This is your dv. You need to calculate this for the whole mass, right? So you need to integrate this over the entire ring. Integrate this over the entire ring. Now the quantities which will not change when I change dm, like when I take different masses, the quantities which will remain the same can come out of the integral, right? So g is a constant that will come out of the integral. Will under root r square plus x square change? No, right? Because you take any mass, it will be at the same distance root r square plus x square from that point. Like even if I take this mass, even this will be at a distance under root r square plus x square. So that also won't change. That also will come out of the integral simply. So I just have to integrate the mass, and that is nothing but the mass of the spring, ring, right? That's why this problem was quite simple. So it's minus gm by under root r square plus x square. Simply this. This was the problem. And you can always draw its graph and all, right? So drawing its graph is not very difficult. So at a distance x equal to 0, the potential is, so if I draw a graph at a distance, if I draw a graph of potential versus x for this, at a distance x equal to 0, the potential is minus gm by r, right? So this is minus gm by r. And don't get confused, why am I taking a negative sign above, right? So the entire v is negative. It automatically means that there is a negative sign implied to it. So I'll start from here, v. And then as x tends to infinity, the denominator will tend to infinity, right? So this should be negative of something, right? So if r square plus x square has to be 0, then r square will be equal to minus x square, and then x will be r into I, some complex number, right? This is not possible, right? You can't have a denominator 0 in this case. That means it is continuous, and it's continuously tending to 0. That means it will be something like this. This is the potential versus x function, right? Don't get confused with the graphs. Look at the graphs in the options, substitute the values, and check how the graph is behaving, and then choose the simplest graph. That is how it is. Don't get confused with as to like this graph might assume different shapes and stuff like that. That all that confusion comes, but like be careful about that. So the second question is even more simple. So I have a square of side A. There are three masses here, and I need to find the potential at this point O. Right. This is the first point, second point, third point. So this first body, second body, third body. Potential at O is nothing but you simply have to find the individual potentials and add them up. So potential due to first body plus potential due to second body plus potential due to third body. What is the potential due to first body? Minus gm by this distance, which is A. What is the potential due to third body? Minus gm by this distance, which is A. What is the potential due to second body? That's slightly different. So this is V1, this is V3. Or what about V2? Now this will be your distance, right? And this is root 2A. Simply applying Pythagoras theorem. So you'll have a minus gm by root 2A. The answer is minus gm by A into 1 plus 1 by root 2. Sorry, 2 plus 1 by root 2, because those two will get added. This is the answer. So once again, a simple problem. And I can also ask you different questions pertaining to the same example. So what if I ask you what is the field at the point O? Right, I won't calculate it, but you calculate it yourself, because the session is not on field, it is on potential. So this will have a gravitational field on this in this direction. It will try to attract, right? So the field for a mass is always towards it, right? It is not away from it, because mass is not a positive charge. This itself will have a field in this direction. So this resultant plus this is the new resultant. So calculate this, get the resultant, add that to the field due to this. Well, so the next question goes like this. I have a hexagon like this. A, B, C, D, E, F are the vertices. You have four masses here, M, 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 and M, placed at A, B, C, D, right? There are four masses, one at A, one at B, one at C, one at D. And the side of this hexagon is A. You need to find the gravitational potential at the center O. So once again, I hope you realize it's the same problem as before, just that you'll have a different geometry now. So this is your first body, second body, third body, fourth body. And in fact, this time each body is equidistant. So each body is at equidistant, each body has the same mass, so each body will have the same potential, right? So the potential at O is V1 plus V2 plus V3 plus V due to 4. And because same mass and each mass is at the same distance from O, I can simply calculate potential due to 1 and multiply it with 4, right? So what is the potential due to this mass? This is A. Remember, because this is a hexagon, look at this triangle now. This side is A. These two sides are equal, right? These two angles are equal. What about this angle? This angle is nothing but 360 total divided by, it's divided, like this is 1/6 of the angle, right? Because there are 6 parts. This is the first, second, third, fourth, like 1, 2, 3, 4, 5, 6. This is 1/6 of 360. That means it is 60. This is 60 degree. And these have to be same. That means even they have to be 60. That means this is an equilateral triangle. That means this side also is having a edge length A. So you have a mass, you have a point, distance between them is A. The potential due to 1 is simply minus Gm by A. And you just need to multiply this with 4 to get the net potential. It's minus 4 Gmm. Sorry, minus 4 Gm by A. About field, once again I won't calculate the field. I would leave it as a task for you. In fact, let me do it for this case, because right, this is simple as well, but you might slightly get confused. So like, remember, this is the point. These two masses, like this one and this one, are having the same value. They are at the same distance. This will try to attract here, this will try to attract here. So these two fields will mutually cancel. They won't have an effect, right? It is as if these two masses are not there. I just need to calculate the field due to this mass and due to this mass. Field due to this mass will be in this direction. Field due to this mass will be in this direction. The angle between them is 60. Will these two forces have, will these two fields have the same value? Yes, because the mass is the same, the distance is the same for both. So field due to 1 is, so field is represented by G. So G due to 2, this is 1, 2, 3. So I'll calculate due to 2. It's nothing but Gm by A square, right? Gm by A square is the field due to 2. Field due to 3 will also have the same magnitude. I'm talking about the magnitude here. It will have the same magnitude, Gm by A square. You have two vectors of this magnitude each. The angle between them is 60. You just need the resultant now, right? So the resultant is nothing but Gm by A square whole square plus Gm by A square whole square plus 2 into Gm by A square into Gm by A square into cos of 60. Right? A square plus B square plus 2AB cos theta, where your A is equal to B, right? So 2 and cos 60 will get cancelled. So it's nothing but 2 into Gm by A square whole square plus Gm by A square whole square. So it's simply Gm by A square, take it out of the integral, out of the root, it's root 3. So root 3 Gm by A square is the field at the center due to all of these masses, right? And what is its direction? its direction is form a parallelogram using this and this as the edge. The diagonal of this parallelogram, like this is the direction of this field, right? The diagonal of the parallelogram formed by these two edges. It's simply vectors, basically, nothing else, right? So with this done, let's look at one more problem now. So let's discuss this case, that of a solid sphere that I was discussing. One problem on this, right? So you have a solid sphere of mass m, right? Radius capital R. At a distance d from the surface, this is d. At a distance d from the surface, at what distance d? The question is, at what distance d from the surface is the potential same as that of r by 2 from the center? The question is not as simple as it looks, because you have a solid sphere here. If it was a hollow sphere, the question was very, very simple. But what if it is a solid sphere? So at a distance r by 2, you need to calculate the potential at r by 2. And that potential has to be equal to V of r plus d. That is the question. What is this d? To calculate this d, I first need what is r by 2. Right? What is Vr by 2? That is the first question. So to calculate this Vr by 2, you need to know the formula. You need to know the formula for potential at a distance r inside a solid sphere, right? And this was something that I asked you to derive, right? I told you the method and I asked you to derive it. So in fact, I would like to give you the formula here, because I've asked you to derive it. You can always obviously verify once you derive it. So I would write the formula here. V at a distance small r is nothing but minus gm by r cube into 1.5 r square minus 0.5 small r square. So if the radius of the sphere is r, if its mass is m, then this is the formula at a distance small r from the center, right? Derive it using the method that I told you. Then look at this. It's not difficult actually. This first term, when you open up this bracket, this first product is nothing but, so in fact you can't really look at it like this. When you calculate the work done to bring 1 kg mass from infinity to the surface and then from surface to inside, when you sum them up for 1 kg mass and ensuring that you do it very, very slowly with an external force, this is what you'll get, right? And that is what I told you to derive. So I would leave you with this formula and then derive it yourself. So at a distance r is equal to capital R by 2, I just need to put capital R by 2 in this formula, right? So that will give me minus gm by r cube into 1.5 r square minus 0.5 by 4 into r square, right? So this is nothing but, so I would leave it like this, don't even need to touch it. I just need to equate this. To minus gm by r plus d whole square, because that is the objective of my question, right? So if I have this mass and this d is outside, right? So from the center the distance is r plus d. So from here at a distance r plus d, I need the potential, right? So I can assume this mass to be at center because it's outside, because this point is outside, right? This is not square here, you just have this potential, right? So you can assume this mass to be at center and calculate. So minus gm by r plus d is what you'll get, and you just need to equate these two, right? Solve this, and the value of d that you will get from here is nothing but right. So in fact, when you actually try solving it, you will get d to be something negative or something, like it will not exist. That is the answer given in the book. It won't exist. So I hope you understood the method, right? So the calculation is not something that I have to teach you. I have to teach you the method. I have to teach you the concepts. So with this problem done, I guess we are done with the session today. I hope you understood clearly what potential means, what are the key terms, when I can call something a potential and when I can't. So with this done, we're done with the session today. I hope you found it informative enough, and then I'll join you for the next session soon. So until then, see you next time. Thanks for joining.